All right, chapter 3 is applications of the derivative. So no longer we're going to look at no new derivative rules. All right, we've learned them all. Now we're going to apply them, and we're going to look at them, and we're going to start off by looking at how they relate to the graph, and then we'll get to applications in the later sections in chapter 3. So first, again, important aspects of the graph. The derivative can be used to determine when a function is increasing, decreasing, and when it might have relative maximums, minimums, and eventually absolute maximums, minimums. So first, the first big concept in 3.1 was finding, again, you should have watched the My Lab videos already. They kind of explain this in more detail. The critical values are the first thing we have to find. All right, a lot of times with the critical values, the hard part is the algebra. We've actually done half of these already. Critical values are sort of important aspects of the function graphically. They're very special points on my function where the derivative is 0, meaning there's no rate of change, no growth. I have horizontal tangent lines, which we found those, again, in previous sections, so we kind of practiced them there. So we've done the horizontal tangent cases. The new one we're going to talk about is we're also going to determine when the derivative is undefined, right, it does not exist, at a point in its domain. All right. Again, they're very special points where that happens. They're special points, so we call them critical values because they're critical or special. First of all, in order to be a critical point, the value has to be in the domain of the function. Right? So the value is in the domain of the original function, whatever the original function is. It's a critical number if one of the following two statements is true. So C is in the domain, and at C, I have a horizontal tangent. So first, and that's the one that's the most common, horizontal tangent. My functions come to a stop. My slope is 0, right? So it's come to a stop. There's a horizontal tangent there. The second case is the sort of special case, is when the first derivative does not exist at that value C. All right, so the first derivative is undefined. But remember, C is in the original function. And so what's happening there graphically to the original function is that it will have a cusp or corner, which means a sharp change. Right, at a sharp change, it's part of the function, but the derivative doesn't exist. Or what's happening there is you have a tangent that's vertical. Vertical lines have slopes that are undefined. Derivative finds slope. So if the slope is undefined, so is the derivative. So those are the two things that are happening. Those are still critical moments. Right, because remember, C is in the domain. It's part of the original function. It just happens to not be a part of the derivative. All right, so to give you sort of the shapes that you're looking for where critical values exist. So the critical point is the x value C, where the derivative is either 0 or does not exist. And then the function value at that moment, the y value at that moment. All right, so the shapes that we're looking for. So the horizontal tangent shapes. All right, when the derivative at C is 0. These are the shapes that you should find. They should be something like this. They're sort of a smooth shape. All right, that would be the C value on these. And so again, what's happening at those moments, at that single moment in time, you get a horizontal tangent line, right? The slope at C is 0. And that would be my critical point. That would be the point C, F of C. All right, critical moment. So horizontal tangent case. The special cases. All right, so first the corner case. The corner or cusp. Cusp just means it's a corner that's more rounded. And so the corner cases, again, these are when the derivative at C does not exist. So the first case would be the sharp change. So if I have something like this, a sharp change, or again, that's more of a corner. Cusp case would be something that's still sharp change, but it's more rounded. So you'll see this is more sharp, this is more rounded. There's more of a curve to it. It means the same thing. At those corners, at that sharp change, at both of those types of places, the derivative does not exist. But C is in the domain of the original function of f of x, right? If those represent my function f of x, they're part of the function. There's a function value. There's a point at that moment. C, f of c. I can find it. All right? There's a moment there. but the derivative doesn't exist. All right, those are critical points. All right, when those sharp changes occur. The second sharp change is when I've got vertical tangents. All right, vertical tangents are when I have a shape like this. Not quite the corner there. A little more rounded than when I've drawn it. All right, so this would be the sort of the shape. There's sort of this S kink in it. And there's another S kink in it, and I'll talk about it here. It actually goes to the horizontal tangent case. So I'll come back to that in a second. I forgot about that one. So at this moment right here, sort of in the middle of that S shape, all right, that would be my critical moment. At that moment, I have a vertical tangent. All right, vertical tangents, well, vertical lines, all vertical lines, the slopes are undefined, do not exist or undefined. Well, derivative finds slope, so derivative is also undefined or does not exist. And so that is a critical moment. All right, it is a part of my curve, right? That point exists on my curve. It's in the domain. But the derivative didn't exist. Now, just kind of, I'm going to re-talk about this sort of shape with this S shape. So this is when the S shape is sort of sideways like this. I get a vertical tangent, the derivative doesn't exist, but it's still a critical moment. There's a similar shape in the horizontal tangent case. So if I sort of rotate that 180 degrees, and we get the S shape like this, so there's an up and down S shape. In that middle value, in that S shape, that is also a critical value. My derivative at that moment is 0. My slope is 0. That is still horizontal tangent. So this S shape also can fall in. If it's up and down S shape, it's a horizontal tangent critical value. So every single of these moments that I drew in sort of red here, if I redraw these as red, are all critical moments. All right, so those are the shapes, and so they'd be part of graphs. All right, so they'd be pieces of graphs, and so if these shapes show up in graphs, those are your critical moments. Meaning, either they're the horizontal tangent case, where my slope is 0 and my function stopped. At that moment, I'm neither increasing nor decreasing. I've come to a stop. Or they're the special cases where there's a sharp change in direction. All right, that's a critical moment. Or there's the vertical tangent case, where the slope is undefined. All right, and those are all the moments where we've got critical values. All right, so those are sort of reviewing critical values. Again, the book does a good job. I just wanted to make sure I hit them one more time because they're sort of important, kind of coming from my point of view. All right, then we're going to get into solving some algebraically practicing algebra. So I'm going to stop the video there and pick it up in the next one.